students. They want to receive their PhD during this commencement period.
All right, everyone. Today is our great pleasure to have Maura McLaughlin here. Maura is the Everly Distinct Professor of Physics and Astronomy at West Virginia University. She graduated from Penn State, received her PhD from Cornell, and was a postdoctoral fellow of the Jodrell Bank Observatory. She's the co-director of the Nanograph Physics Frontier Center, and she received numerous awards, including the Research Corporation's Cottrell Scholar Award, an Alfred Sloan Fellowship, an ETS Fellowship, and the Shaw Prize in Astronomy. She also co-founded the Pulsar Search Collaborative Program, which has involved over 2,000 high school students in Pulsar searches over the past decade. We're all very happy to hear about her talk today. Thank you.
Thank you so much. Hi, everybody. It's really great to be here. It's a really nice space. I feel like I've been here once before for a workshop when this building was first built, maybe. It looks familiar, but I have absolutely no memory of like when or what it was about. But thank you for inviting me. This talk is fairly general, you know, and I know there's a couple of Nanograph members in the audience, and I'm not real sure of the kind of general familiarity with Nanograph, so feel free to interrupt me as we go, either if I'm going too fast or if you have some like more detailed questions you want to ask and I'm not going into enough detail. So yeah, I'm going to talk about our recent results on searching for very low frequency gravitational waves using high precision timing of radio pulsars with large radio telescopes like the Green Bank telescope in this little cartoon here. And we think that the most likely source for these low frequency gravitational waves are extremely massive black holes at the cores of galaxy mergers. So I'm going to tell you this story here. If you want to sleep through the rest of the talk, this is kind of like the big picture. So for many years, we've been searching for this very special signature in our pulsar timing data. This dotted line shows the correlation expected in pulsar times of arrival versus their angular separation on the sky if general relativity is correct and we have an isotropic distribution of gravitational wave sources and pulsars. And these blue points here are our most recent measurements from our Nanograph pulsar timing array. This is based on 67 pulsars. And for the first time, we finally have seen this expected correlation in our data, which was really, really exciting. I was surprised actually at all the like media attention this got, because it's kind of an esoteric result, but there were lots of fun headlines like scientists say space-time churns like a choppy sea, or scientists found ripples in space and time and you have to buy oysters. Anyway, so I'm going to talk about the motivation for doing this experiment, how we fit in with other gravitational wave experiments, how pulsar timing works, our recent results, of course, and then what does it all mean? How can we interpret this data? What's that? Oh, yeah. Yeah. Very tight. There we go. Okay. Yeah, so just a little bit about Nanograph. Oh, no, what happened?
Yeah,
Okay. Okay, good. Yeah, so a little bit about Nanograph. There are a couple of Nanograph members in the room. So you have a presence here. Nanograph is the North American Nanohertz Observatory for Gravitational Waves. We were formed back in 2008. There were like a dozen of us when we first formed. Now there's over 200 of us, mostly in the United States and Canada, but also at some institutions in Europe, Asia, all around the world. We are part of a bigger collaboration called the International Pulsar Timing Array. So this is a consortium of all the individual PTA consortia, so Nanograph, and then similar collaborations in Europe, Australia, South Africa, and India. Okay, so why do we care about detecting low frequency gravitational waves? I mean, my primary motivation for getting interested in this about a decade ago was to try to answer a really important puzzle in astrophysics about how galaxies have grown and evolved through cosmic time. So if you look at the first galaxies that were formed, they're small, they're kind of irregularly shaped. And with time, galaxies have grown larger and more regularly shaped. And you're probably familiar with this process of hierarchical galaxy formation, right? So we think this has happened when smaller galaxies merge with other small galaxies to form bigger and bigger galaxies. And there's lots of evidence for this, right? You can electromagnetically see that some galaxies are in the process of merging. But there's a lot of questions about the very last stages of this process. You might have heard of the last parsec problem or the final parsec problem. So the two black holes at the core of this galaxy merger need to get close enough for gravitational waves to push them together, right, to cause their final merger into a single black hole. But how do they get to the separations required for gravitational wave emission to bring them together? There's lots of questions, like what is the role of accretion? What's the role of stellar scattering? But you can't study this electromagnetically, obviously, right? You can look at this image, you can't tell that this galaxy is the product of a merger. The only way to study this is through gravitational waves. That's the motivation for the project. And we can search for several different kinds of gravitational wave sources with our data. We can look for individual supermassive black hole binaries. We can also search for a stochastic background, so the combined signature of gravitational waves from all of these supermassive black hole binaries throughout the universe. And that's the signature that we have evidence for in that correlation curve that I showed you. Just a little bit more background information about gravitational waves. I'm sure you've all heard of gravitational waves. So LIGO has like 100-ish detections of compact object mergers. So these are objects with masses of like a couple times the mass of the sun to 100 times, something like that. There's this beautiful butterfly diagram which shows where all those sit.
So what are these like EM, black holes, EM neutron stars?
They're mostly radio pulsars.
So what is EM?
Oh, electromagnetic, sorry.
Okay.
Yeah, so these are pulsars that are detected with radio telescopes, and maybe a couple other electromagnetic, like point source neutron stars. Okay, yeah, so LIGO did this, that's great. We all love LIGO. Let's review a little bit about how LIGO works, because that I think is a nice introduction to how pulsar timing arrays work, right? So this is the LIGO interferometer. LIGO has two arms that are perpendicular to each other. And as you know, lasers run back and forth along these arms. And when a gravitational wave passes through the LIGO detector, it's going to stretch one arm and squeeze the other, right? So one arm gets a little bit longer, one arm gets a little bit shorter, and then the light travel time along the arms changes. And that is detected in an interference pattern back here, right? So LIGO is an interferometer that is very sensitive to very small changes in light travel time along these perpendicular arms. And they are perpendicular because gravitational waves have this very special quadrupolar perturbation. So if a gravitational wave would come through the screen and we have this ring of test particles, the distances between the particles would change in this very special way. So you can see you're going to get the maximum difference in light travel time for arms that are oriented at 90 degrees. Okay, makes sense? So we want to detect gravitational waves with much, much longer wavelengths than LIGO, with much, much longer timescales, right? And so in order to do that, we need to build a very, very large gravitational wave detector. So we've constructed a gravitational wave detector using pulsars. So pulsars are neutron stars. They're born in supernovae. This is the standard little pulsar cartoon. We have the neutron star here. Pulsars have very strong magnetic fields, so like 10 to the 8 to 10 to the 14 Gauss or so. And particles are accelerated along those north and south magnetic field lines. And when they're accelerated, they produce all kinds of emission across the electromagnetic spectrum. And we study the radio emission. So most pulsars are best studied in radio and timed most precisely through radio waves. Sort of like little cosmic lighthouses, right?
Sorry, I got slightly confused. The gravitational waves you want to detect are not the ones that are produced by the merger of these massive black holes, but like before.
Yes. So we're most sensitive to gravitational waves with periods of something like 10 to 20 years, basically the time span of our data set. So these supermassive black hole binaries are still very far from merger. They're like 1 million years or so from merger. They're non-evolving over the 15 or 20 year time span of our data set. So while LIGO templates, are very exciting, right? You can see a lot of evolution and then the final merger. Our templates are basically just like sine waves for a circular binary. We don't even see any evolution over the time span of our experiment for the sources that we're most sensitive to. So they're just stable supermassive black holes in stable orbits around each other, very slowly, right? Getting closer and closer together, but very far from that final merger.
And this is much weaker than LIGO. So
It is not, because they are really, really massive. So I'll show a plot soon. And we are also sensitive to what we call burst sources, right, which could be emitted when two supermassive black holes merge, but we think we're much less likely to detect the continuous wave, these continuous, kind of non-evolving sources than we are the mergers themselves. I'll talk a little bit about that too. Cool. So the kind of pulsars we use are called millisecond pulsars because they have very short millisecond periods. They're recycled pulsars, so they've been spun up to these very short periods through accretion of angular momentum and mass from a companion star. It's a whole fun story, but I don't have really time to talk about the pulsars themselves. But there's about 350 of these millisecond pulsars, these recycled millisecond pulsars in our galaxy. So our experiment is a pulsar timing array experiment. That means we're observing a network of pulsars distributed across the sky, and we're looking for correlated changes in the arrival times from pulsars in this network. This is a nice little cartoon that illustrates what we're doing. So these are basically the arms of our detector. So while LIGO has 4-kilometer arms, we have arms that are, thousands of light years long. Our test masses, 1.5 times the mass of the sun, whereas LIGOs are, 40 kilograms or something, right? So, but it's the same kind of experiment. It is an analogous experiment. One kind of different thing about our experiment compared to LIGO is when a gravitational wave passes through LIGO, it stretches the entire detector. The wavelength is bigger than the detector. Our wavelengths are actually smaller than the distances between us and the pulsar. So the pulsar is experiencing a different gravitational wave perturbation than the Earth is. So when we do our calculation of the expected perturbation, there's an Earth term and a pulsar term. That's kind of a nuisance in some way, because for this search for this correlated background signature, these pulsar terms are just noise because they're all doing different things. But it's also a huge benefit for a single source. If we can detect both terms of the perturbation, then we can actually see the evolution of a gravitational wave source, which is really cool. We can catch it at 2 points in its evolution. This little diagram shows the correlation that we're expecting. If two pulsars are in the same direction in the sky, we expect correlated perturbations. If a pulse from one of these pulsars arrives early at one epoch, a pulse from another pulsar in the same direction should also arrive early, right? At 90 degrees, we expect anti-correlated perturbations, and at 180 degrees, they should be correlated again, right? Yeah.
And does it show the Earth term or the pulsar term, or like a mix of those?
So basically, this is, you can think of the Earth sort of here at the center, and this shows, this is.
Yeah, I mean, is it the Earth term or pulsar term, as you name it?
This diagram here, I mean, this is showing what the Earth term should look like.
The Earth term,
Yeah.
right?
Yeah. The pulsar terms are just, the pulsars are doing different things.
Depending on the distances
Yeah,
of the
depending on
pulsar.
the distances. So this is what we see from the Earth looking at pulsars in different directions. Yeah. And when you do the math, then it looks like this. So this is the Hellingsen-Downs curve. This was calculated back in 1983. It's very well known. The maximum correlation is at 0. There's a dip at 90, a peak at 180. It's not perfect. It doesn't look as intuitive as those little cartoons. And this happens when you just average over this whole distribution of sources. But this is a very clear prediction for what we should see for an isotropic stochastic gravitational wave background, assuming GR is correct. The maximum correlation will only be 0.5 because these pulsar terms are all uncorrelated. They just add noise. So this is pretty cool. Like when we make this detection, we're actually detecting the effect of gravitational waves on the Earth itself, right? That is what we're seeing. So just a couple of plots that just put us in context with other gravitational wave experiments. This shows gravitational wave frequency and characteristic strain, and LIGO, of course, is up there, right? So LIGO is sensitive to very high frequency gravitational waves, events that happen on time scales much less than a second. Nanograv is way down here in like the 10 to the minus 8, 10 to the minus 9 frequency range. And the reason for that, again, is because we are most sensitive to gravitational waves with frequencies of 1 over our data span length. And our most recent data set was 15 years. So that's like between 10 to the minus 8 and 10 to the minus 9 frequencies. To get a rough estimate of what our strain sensitivity is, you can take the approximate average timing precision of our pulsars. It's about a couple hundred nanoseconds over the time span, and that's about 10 to the minus 5. That's a good kind of characteristic strain sensitivity. So we're sensitive to only much larger strains, but these supermassive black hole binaries are extremely massive, so they produce a very bright gravitational wave background. The background we expect to see, the stochastic background, we expect it to be very red, right? So much more power at low gravitational wave frequencies. This is a little cartoon illustrating what it might look like. The reason for that is that even though for one particular gravitational wave source, you would have a higher strain for a higher frequency binary, there are many more binaries in the low frequency part of the spectrum. They spend more time moving through that part of the spectrum. So there's more gravitational wave power at these lower frequencies than at the higher frequencies. Okay, and these are obviously cartoons. It's just to illustrate that we expect there to be individual supermassive black hole binaries and also this red stochastic background spectrum.
What is the wavelength for your optimal frequency? Your most
Yeah, so around our most sensitive frequency, we're looking at wavelengths of like parsecs, something like that.
and how does that compare to the distance to the pulsar?
It's much, much smaller. Yeah, so the pulsars are at, say, kiloparsec, roughly-ish distances, or, you know, 1,000-ish light years or so. And the wavelengths are much smaller. They're sort of at around a parsec or so. It's actually a very good question.
But could you explain
Because-
why? You would have thought that naively that the distance would set the optimal frequency, but why?
Setting the optimal frequency is the time span of the data. So we're analyzing 15 years of data. And so we're most sensitive to frequencies of like 1/15 years. Right,
So
so,
if you analyze.
and we're also sensitive,
If we were to analyze the 15,000 years.
yes, it would. Yeah. The longer we analyze the data, so, and you can see that here, like here's our 2020, why is that up there? I don't know why that's. Here's our 2020 sensitivity curve, and here's our 2030, and you can see that in those 10 years, our most sensitive frequency has marched to the left. And we get more sensitive with time. We also, with time, because the spectrum is red, get kind of like a double benefit because the background also grows as we go to these lower frequencies. And I don't have time to talk about pulsar distance measurements, but your question is a really important one because in order to include these pulsar terms, when we search for single sources, we need to know the positions of the pulsars to about a gravitational wave wavelength. So about like parsec accuracy, which is actually really tricky. So it's not unimportant what the wavelength to distance ratio is, because that sets a goal for distance measurement for our pulsars in order to unambiguously include these pulsar terms and correct for all the delays appropriately between all the pulsars. Does that make sense? Yeah,
But
Priya.
also, Maura, as we collect more data over years, don't you become more sensitive to a larger range of binary separations also?
Yes. Yeah. Yeah.
So you start picking up in terms of the separation distribution of binaries, you start getting closer end ones as well as further. So you get a bigger range, right?
Yeah, exactly. Yeah. So we're not only sensitive to, we're only sensitive to 1/15-year orbital period binaries. We can detect binaries up until like 1/the cadence of our observations, which is, roughly monthly or so. So we can detect much higher frequency binaries. We are just less sensitive to those higher frequencies. And no one has asked, but this spike here is at 1/a year, because we would fit out yearly periods when we fit our pulsar timing model, because the pulsar position is also a yearly signature in our timing data. Magdalena?
Yeah, just related to this, I wanted to ask, how long do you think we'll have to observe to pick up a turnover in the spectrum?
What a good question. Yeah. So at some point, this is obviously very idealized, right? At some point, we expect this spectrum to turn over due to environmental effects like accretion, stellar scattering. Now to 100 years from now, I mean, it's kind of like wide open. There's some hints we might even be seeing it now. Let's leave that conversation for when I show our actual spectrum, because there's already a hint that our spectrum is a little bit shallower than expected due to purely gravitational wave driven evolution. So we may already be seeing some hint of a turnover.
Sure.
The question back there.
Yeah, I was just wondering, like, one parsec accuracy for distance is great, very good. How do you get so high?
So,
Can you solve for it?
yeah, so parallax
Okay.
measurements. So we can measure parallaxes for pulsars in two ways. One through VLBI for interferometry, and another through the pulsar timing itself. It's actually very tricky, as you point out, to get that level of accuracy. So there's one pulsar that we're doing it for now, a very, very bright, very, very nearby millisecond pulsar. It's only about 200 parsecs away, and it's really, really bright. But with time, we will start getting more and more of those. So in, I don't know, a couple of decades, we should be able to include distances to, I don't know, maybe a dozen pulsars. It just takes patience to measure these parallax signatures accurately enough.
Just to clarify, you don't really need the distance because you're throwing away the pulsar term.
Yeah.
Isn't it?
Well, for the stochastic background, yes. For the stochastic background, we don't care at all. Even if we knew the distances perfectly, it wouldn't even matter.
Right.
For that, we don't care. But for single source detection, we can do it without the distance.
Yeah.
So right now we're searching for single sources. We basically set a prior on the distance. We can either search over this prior range or just not include the pulsar terms. There's two ways to do it, but it's too expensive to search for all the distances accurately to basically like phase up the whole pulsar array, right? But if we knew the distances, then we could unambiguously kind of like phase up the array, and that would allow us to localize gravitational wave sources very, very well, which would be very exciting.
Yeah, a short question on this was, the stochastic background, is it formed by the same kind of sources as like separate supermassive binaries, just like that are less heavy, or?
Yeah, I'm going to talk more about this.
Again.
I like questions, but so the kind of like for sure thing that we think is contributing to the stochastic background are these supermassive black hole binaries. Like we know galaxies merge, we know they have black holes at their core. There's other things that could contribute to it as well. We could have gravitational waves from early universe inflation. Cosmic strings produce gravitational waves. There's like hundreds of papers of lots of sources for low frequency gravitational waves, many of which I don't understand. I mean, lots of, like domain walls and I mean, many constructs.
But it includes the supermassive black holes, right?
It certainly includes
Yeah.
supermassive black hole binaries. The universe would have to be crazy if there wasn't a contribution from the supermassive black hole binaries.
I mean, it also would be fair to say that you think that's the dominant contribution.
Yeah, it's got to be the dominant contribution unless we live in a very strange universe. I think there are some theorists who are still holding out that it's not the dominant contribution. There's some cosmic string folks who still think it may be mostly cosmic strings, but I think that's a minority opinion. Okay, we are definitely going to go a little over, so I'm going to try to speed up through the pulsar timing stuff. So a little bit about our program and how we actually observe the pulsars. So we need very large radio telescopes to do our experiment. Pulsars are weak sources. The 15-year data set that I'm going to talk about today is predominantly Green Bank Telescope and Arecibo Observatory data. And we cut the 15-year data set off the day we lost access to Arecibo. So it was just a very nice natural stopping point. So we stopped it the day we lost access to Arecibo. Since Arecibo collapsed, we are trying to compensate for its loss with more time on the Green Bank Telescope. And we're now also incorporating data from the Chime Telescope in British Columbia. And we have a small program on the Very Large Array in New Mexico and an even tinier program with the FAST Telescope in China. But there are some pulsars that we were observing with Arecibo that we just can't observe anymore because Green Bank doesn't have the sensitivity. So we observe 70 pulsars right now with the Green Bank Telescope, about 50 with Chime. At Green Bank, we observe about once a month. And so every time we observe a pulsar, we'll sit on it for a half an hour or so. The individual pulses are very faint. So we sum up every individual pulse over that half an hour. We call this folding. So we know the period, we sum them all up one on top of the other. And that gives us a very high signal to noise profile at a particular epoch. We measure the time of arrival of the profile at that epoch. Then we go back a month later. We do the same thing. We measure another time of arrival. And we have a timing model that incorporates all of the known astrophysics. And we will go and subtract when the pulse arrived from when the pulse was predicted to arrive. And we call this a timing residual. right? So it's just the difference between when the pulse arrived and when our best model predicted it should have arrived. And it's these residuals that we search for gravitational waves in. You can go download our data at data.nanograv.org. Our most recent data set is all public. You would get stuff like this. You'd get a text file with a whole bunch of times, an MJD format like this. These are radio frequencies, MJDs. These are what we call TOAs, or times of arrival. You get profiles. This is a pulse profile for one of our brightest pulsars. There's linear and circular polarization information in here. Those are the different colors, like very high signal to noise profiles. So much science that one could do with these in addition to pulsar timing stuff. And then we get a timing model which looks like this. So these are all like the known things that we fit for in our data. So things like position, proper motion, obviously spin frequency, frequency derivative. Here's that parallax term. This is in a binary with a white dwarf star. The orbital period is about 67 days. These are all the binary parameters. Some of these are general relativistic corrections. So each pulsar will have a timing model that looks like this. And I'm still amazed, like even now, when I look at these frequency measurements and the precision to which we can determine the spin frequency of a pulsar on a particular epoch. It's pretty impressive, or the positions for that matter. Okay, so the way Nanograv works is we put out data releases every few years. So we accumulate data for a few years, say, okay, let's release that data. And at the same time, let's do a gravitational wave analysis and also publish the results of that analysis. And so this is the history of our data set since our 5-year data set in the very beginning to our 15-year data set now. These are pulsars along this axis. And you can see with time, we've just added more and more pulsars to the array. So a big part of our project is searching the sky for new pulsars that we can add to our pulsar timing array. And this makes us much more sensitive. The different colors are different radio frequency telescope combinations. And so these are examples of some of the residuals from our 15-year data set. So these are the actual data that we will cross-correlate to search for gravitational waves in. These are 3 different pulsars. The different colors are different radio backends and telescopes. These 2 pulsars are observed at both Arecibo. Those are the A and P backends, and at Green Bank, those are the G backends, and the 1.5 gigahertz L, whatever, those are different radio frequencies. So you can look at these and, you know, at first they look pretty good, right? Like this is 15 years of data, and these residuals are generally consistent with 0, right? The error bars generally cross 0, which means our timing model is doing a good job over 15 years of predicting when pulses will arrive. And this is 1 microsecond here, or 2 microseconds from here to here, right? So that's like pretty good for a pulsar with a period of a millisecond. However, you can also see that they're not featureless, right? They're not perfect. There are some individual points that lay off of 0. Maybe you could look at this and imagine you see some kind of what you might call red noise, right? Some like low frequency noise. And the only way to know if anything we see in these residual plots is gravitational waves or something else is by doing this cross-correlation analysis and looking for this correlated signature with their angular separation. Yeah, so most of our pulsars, the root mean square of these residuals ranges from like 60 nanoseconds. That's our best one, to about 1.5 microseconds or so. So that's kind of like the level of timing precision that we get. So what would a gravitational wave look like in those pulsar timing residuals? Let's start with the left-hand side of this. So if we just took one of those pulsar timing residuals and we injected a stochastic background, that stochastic background would have most of its power at very low frequencies. And so if we just injected it, it would look like this. These 3 different colors are just 3 different pulsars in different directions. It would be a very long timescale perturbation to those residuals. Most of the power is at frequencies, very, very low frequencies. However, this bottom plot shows what a stochastic background looks like after we fit our timing model. So when we fit our timing model, we absorb a whole bunch of this low frequency power, and we end up getting something that looks just kind of like noise. We would call this red noise, right? So kind of like quasi-periodic noise with some characteristic frequency structure, but different in phase, amplitude for different pulsars, right? Because we'll absorb lots of those gravitational waves into our timing parameters. There's no way for us to avoid doing that. On the right is what we get for a single gravitational wave source. So for a particular supermassive black hole binary in a particular direction, these are the signatures we'd expect for 3 different pulsars in different directions. And so you can see they all have the same period. They're going to have different amplitudes and phases, and that depends on the angle between the Earth and the gravitational wave source and the pulsar. And unless that binary has a period of like exactly a year, or exactly 67 days in the case of that pulsar with a white dwarf companion in a 67-day period, it's just going to survive because we're not going to absorb that into any other parameters.
So you mentioned previously that we can potentially observe the evolution of the gravitational wave
Yeah.
source if we look at different
Yeah.
pulsars. So here in this example, there would have been no significant evolution. That's why the periods are the same between the two pulsars. Or am I misunderstanding?
No, you're not misunderstanding. So yeah, so this is kind of a simplification. So this is just the Earth term, just one term of the perturbation is shown here. So there's no evolution because we're not observing over a long enough time span. In real life, there's also a pulsar term perturbation, which would be like another sine wave kind of superposed on this sine wave, because that would have well, actually, sorry, let me make sure I'm getting it right. The pulsar term would have left earlier than the Earth term. So the pulsar term would actually be a longer period than the Earth term, but you'd see like two sine waves basically, which I know is not exactly your question. Does that make sense?
I think it does.
Why, especially the blue line, it's kind of like definitely changing over the time. So it's like increasing in amplitude.
It's evolving a little bit. I did not make this plot. This is from a review by Uris Verbies. It does seem to show like a little bit of evolution.
Mhm.
I don't know if that's really right. Like we shouldn't.
Okay.
Like they should. If one of them is evolving, they all should be evolving. So I don't think that's quite right. But yeah, it's not my plot. Okay, so just a little bit before I talk about our results. So far I presented kind of a simple picture, right? Like we have this gravitational wave that looks like noise. We have all these deterministic pulsar timing terms. We can distinguish them really easily. Well, unfortunately, there are other sources of noise that we can't fit with the timing model. These are some of them, right? So the pulsars aren't perfect spinners. They may have some underlying like rotational noise. Pulse jitter, this is like single pulses don't always keep phase. There's things due to the interstellar medium like scattering and DM, planetary ephemeres that we need to correct our times of arrival to the solar system barycenter to an inertial reference frame. Those could have errors. There could be errors in our clocks at the observatories, all sorts of things. The point of this is just to show that we can distinguish them all from gravitational waves because they have different characteristics, right? So this stuff depends on radio frequency. It's not achromatic. This pulse jitter is what we would call white noise. It's not correlated in time. Planetary ephemeres would produce a spatially correlated signature, but it wouldn't be quadrupolar like the gravitational wave background. It would be dipolar. So we have a model which distinguishes all these different sources of noise from the gravitational wave background. This is what one of these models gives us. So this is an example of our noise analysis for a particular pulsar. So what we do is we measure the basically like noise power, right? The spectral power at a bunch of different gravitational wave frequencies. So these orange bands shows the posteriors on that spectral power at a bunch of discrete gravitational wave frequencies. And then we try to fit that with what we call a noise model. And so our noise model is very simple. There's this common red noise term, is red dotted line here. So this is a noise term that is fixed to have the same amplitude and the same spectral index for all of the pulsars. It has to be the same in every single pulsar, same amplitude, same spectral index. There's nothing about correlations, spatial correlations in here at all yet, right? This is just a common source of noise with the same amplitude and spectrum. And then for each pulsar, we also allow another red noise term, which is independent to each pulsar and would account for, say, intrinsic spin noise. And then we fit for a white noise term, which is here. And then all together, they sum up to this total noise. This bottom plot shows the Bayes factor for excess noise versus frequency. So this is telling us that we're modeling the noise well. If these Bayes factors were bigger than 1, that would mean that we had excess noise at some of these frequencies that wasn't well modeled by this combination of intrinsic noise, common red noise, and white noise. Okay, getting a little bit in the weeds here, but I just wanted you to see like what it is we actually do. This is another pulsar, which isn't quite so good. It says the pulsar on the previous slide is one of our very best timers. It is our best timer. This is the 60 nanosecond one. It has very little intrinsic noise. It's much lower than the common term. This pulsar is a little noisier. Its intrinsic red noise is actually brighter than this common source of red noise, right? But we can distinguish those two because this is fixed to be the same among all the pulsars. This one is left to vary. Makes sense. And we're doing a good job modeling them. We can see here with these base factors that our noise model is sufficient to fully explain this gravitational wave spectrum.
So basically this noise, the excess base factor way is basically showing that there isn't some other
Yes.
noise term that's not accounted for.
Mhm. Yeah, it's basically asking, is the measured noise greater than the noise modeled through these fairly simple noise modeling terms? And the answer is no. I was actually surprised by this because the noise model is pretty simple, but it does a good job explaining the noise. And probably with time, it may need to be more sophisticated, right? Okay, so I'm like running a little behind. Let me whiz through the actual results of our gravitational wave analysis. So a tiny bit of history. The first 3 gravitational wave analyses that we did in our 5, 9, and 11-year data sets all resulted in upper limits. We did not see any common source of noise, nor any spatial correlations. And so all we could do was set an upper limit on the gravitational wave background. Our 11-year limits were pretty interesting, and they actually constrained some models for supermassive black hole binary evolution. We also had some issues that came up with the solar system ephemerides. The ephemerides that we get from JPL were not accurate enough for this analysis. And when we first did the analysis, we actually detected a very significant common noise source. This is the amplitude of a putative gravitational wave background. This is the probability distribution. And when we first did it, we got curves that looked like this. We thought we detected gravitational noise. We were very excited. There's this common source of noise. This is so great. And then we used different ephemerides from JPL. These are 4 different JPL ephemerides, and we got a different answer every time, which was very worrying. And then once we corrected for the ephemeris in our analysis, we developed this code called BaseFM, which basically fit for the errors in the ephemeris at the same time as it fit for gravitational waves. Then we got things that just look like but it was a fun little exercise because we went through like the detection process, and we also went through this process of we see a signature, like let's see if we can make it go away, and we could.
Yeah, so you said that the influence of ephemeris would be like dipolar, not quadrupolar, so it still somehow can mix up with the like.
Yeah, so that's a really good question. So in the 11-year data set, we just didn't have enough sensitivity to discriminate any spatial correlations. Like all we saw was this common noise source. So we couldn't discriminate a dipolar from a quadrupolar spatial correlation, right? All we really saw was this common noise. So at first we were just really excited. There was no evidence for it being dipolar or quadrupolar, but we just saw that there was this common spectral process, which was cool, but it was this ephemeris error. So fortunately, we don't need to worry about this ephemeris error anymore because of Juno. The error was mostly dominated by uncertainties in Jupiter's mass and position. Now the Juno mission has blown those all away. So the new ephemerides are great. In our 12.5-year data sets, that's our last one, we detected a very significant source of common noise. We detected it regardless of this ephemeris issue, whether we fix the ephemeris at the JPL one, this is an ephemeris from a French group, or whether we do the Bayesian fitting. That was really exciting. The Bayes factor was over 10,000 for a common noise process versus noise that was independent to the individual pulsars. So when we saw this, we thought this has to be gravitational waves, right? What else could this be? What other common process could there be? However, when we searched for spatial correlations, we did not see them. There was no evidence for any kind of spatial correlations in the 12.5-year data set. This is the best fit to the Helmings Downs curve. These are the bin correlations. These are not the actual correlations we analyze, right? We look at every single pairwise correlation. This is just bin to kind of guide your eye, but you can look at that and see, okay, that's not really matching that line. Yeah.
I'm just trying to understand this. You have Bayes factor of 10,000 for the common noise term versus one of the questions I had was how you disambiguate between the two of those things generally before you account for these correlations. It sounds like that's the first step, is just to look at the magnitude of the noise. And is it just a matter of how many pulsars you have, and if you have a sufficient number of them, it's just sort of there's a probabilistic argument in favor of it's more economical for the model to model them all with one common noise term than many independent terms?
Yeah, exactly. So modeling, I mean, you could model them all with just one source of noise and no common noise, and that would be sufficient. But we have all these different models of just independent noise or independent noise, plus this additional spectral process that's common. And just statistically, it's much more favored to have this one common statistical process in addition to all of the independent noise terms. Does that make sense?
I think it does.
We can talk more about it.
Yeah, I think it depends. Again, it seems like it depends on an assumption about how independent you expect them to be, but it seems very reasonable to me.
Yeah, we could talk more about the specifics, yeah. Yeah, so no gravitational waves. However, all of our collaborators also saw this common process in their data, which was really exciting. So this is the Australian collaboration, the Parkes Pulsar Timing Array. They saw a common process with a similar amplitude and spectral index to our process. The European Pulsar Timing Array saw a process with a similar, just to be awkward, they plotted it on different accents, but similar amplitude and spectrum to our common process. And then we formed a big combined international data set with all of these data sets together. And we see a similar amplitude and spectrum. And in this particular data set, the common process is preferred over independent noise by 10 to the 8, base factor 10 to the 8. So huge, right? And again, I'm really running out of time, but I'm getting to the punchline. Because of this, right, this was very exciting. We all had seen this same common process in our data sets. We got together and we said, let's do the next stage together. Instead of just publishing independent analyses of the next data sets, which should perhaps reveal these spatial correlations. Let's sync up our processes, let's work together to publish all of these papers from all the different data sets in a simultaneous way. This was really hard work. Priya was on a detection, she was on our detection committee and can testify that it was really hard work because there were lots of just different people, different analysis techniques, different ideas about how to do the analyses. But on June 29th, 18 papers simultaneously appeared on the archive announcing the results of this gravitational wave background search for nanograv, the EPTA, the PPTA, and also the Chinese PTA, and then a whole bunch of like ancillary science papers from nanograv, the EPTA, and the PPTA. And we did not sleep much in the kind of January to June
for several months
period of that year. It was really, really hard work. It resulted in this plot here where you can see that, it may not look like much, right? The error bars are still kind of large, but when we saw this, we were extremely excited because it shows this hallmark positive, negative, positive correlated signature that we had been looking for 15 years. So this is really exciting. You may look at that and ask, how significant is it? It's about 3.5 to 4 sigma significance. There's a bunch of different ways you can estimate the significance of a signal like this. We generally try to do this like just empirically, right? So taking the pulsar timing data and just shifting the pulsars in phase with respect to each other, which should just remove the correlations. And then you do that, 10,000 times and say, how many times do we have a correlated signature that's as significant or more significant than what we saw? We can do that in a Bayesian or a frequentist way, and I don't really have time to go into this in too much detail. But basically, it's about like 3.5 to 4 sigma. So you'd expect something that's significant in like 1 in 1,000 to 1 in 10,000-ish realizations. I think I am very confident calling this a detection because we have seen this in our data, and our collaborators have also seen similar things in their data. And it also kind of behaves like we expect, but it still hasn't met that kind of 5 sigma criterion that, say, the particle physics community has for a detection. So we, in our paper, have called this evidence for. But our next data set should result in a, bona fide detection. So next signal does what it should, right? So we did lots of tests to make sure that this wasn't just some like statistical fluke, but as we add more data, as we add more pulsars, the signal to noise of the signal grows as we expect. Of course, we did lots of tests, like looking at different subsets of data. We look at just the Arecibo data or just the Green Bank data. We see it in both data sets. It's not something specific to say like one telescope. So we did all these kinds of tests. This is the spectrum. So these gray bands here are these violin plots, right, which show the spectral posteriors. The more interesting thing, I think, is this blue band, which is a fit of a power law to our spectrum. And so you can see it's red. There's more power at the low frequencies. This is what you expect for a population of supermassive black holes, this black dotted line, if they're evolving purely due to gravitational wave emission. So we're a little bit shallower than that. So maybe we're already starting to see some kind of spectral turnover, but there's obviously huge errors here. It's hard to say. But the basic point of this is it is consistent with a population of supermassive black hole binaries. However, it's also consistent with lots of other things. It's consistent with gravitational waves from early universe inflation, cosmic strings. And it's interesting, if you look on ADS and look for like the number of papers written about the supermassive black hole binary hypothesis versus all these other things, the other things outweigh the supermassive black hole binary hypothesis by like hundreds to one. And our new physics paper that talks about all these other things is much more cited, like much better cited than our supermassive black hole binary paper. So this is, there's lots of speculation about this signal. So it's consistent with the signal seen in the other PTAs. So this process of coordinating the publication really paid off because we all see consistent things, consistent amplitudes, consistent spectra. Our data sets are mostly independent. These are the number of pulsars. So this is the nanograph pulsars, the Australian group, the European group. Some of the pulsars are in common, so they're not like totally independent, but they're independent telescopes, independent observing systems, and to some extent, independent analysis methods. So it's 11:50. So let me just wrap up by talking a little bit about, what can we say, right? So I started off saying a motivation was to try to understand.
Well, just
Yes.
before you continue.
Of course, yeah.
The 3.5 to 4 sigma.
Yeah.
Is by combining all of the data, right? Or it's not,
No.
is it just that?
Just nanograph. So
So shouldn't you get this extra factor you need to combine it?
we will. Yeah. So combining all the data is really hard. It's really complicated because they're taken with just all these different observing systems, different ways of fitting for things like dispersion measure. Like there's lots of subtleties that make combining the data difficult. So nanograph first saw the signature in our data about 3.5 years ago now. We saw this spatially correlated signature and we had a decision to make, right? Either we just go alone and just publish it, or we go the other way, as you suggest, and wait till we have a proper, fully combined data set, or we do in the middle, where we work with our international colleagues, everyone analyzes their data sets independently and we sync them up. And we did the middle thing. We're now doing the full combination thing, and I'll talk more about that. So for sure, the signature should be incredibly bright in this combined data set. It just took a really long time, and we didn't want to wait like another 2 years to publish our results.
Okay.
Although we probably would have published it by now, honestly, if we had done that, probably about now we'd be publishing it because it still took a really long time to sync up even the independent data set analyses. So what can we say about supermassive black hole binaries? So the general way that we try to, that we carry out this analysis is we simulate populations of supermassive black hole binaries, and we assume things like a merger timescale, like a pair fraction, what fraction of them have a pair of black holes, a galactic stellar mass function, a black hole bulge mass relation, right? So there's lots of literature that predicts various, quantities for all of these astrophysical variables. And then we push them through an evolution package. One branch is just gravitational waves. One has things like an accretion disk and then, different properties of that accretion disk. Anyway, and at the end of all this, we come up with simulated gravitational wave spectra, and then we compare those simulated spectra to our measured spectra. And that is how we place constraints on black holes. And we can produce plots like this. So the solid lines here show the gravitational wave background fraction coming from supermassive black hole binaries of particular masses, mass ratio, redshifts, right? And so you can see the posteriors are still like really big. And there's lots of covariances between all of the different things in our model. But generally, we need pretty massive black holes, like billion solar mass black holes, nearly equal mass ratios. We think they're at redshifts of say, 1 or so. I don't have much time to go into a lot of details about these, but I'm just going to power through. These are some of the other quantities that we can constrain using this kind of analysis. The gray bands here are the posteriors. This is versus gravitational wave frequency. Sorry, these are the priors. The gray bands are the priors, the blue are the posteriors. So our models generally prefer, like we need higher mass binaries than most models predict, for instance. Another way of looking at this, these are all the papers that have published predictions on what this gravitational wave background should look like, what the amplitude should be. This is the amplitude, and these green bands are the predictions for different papers. There's our result. So you can see we're not inconsistent with prior predictions, but we're at the upper end of the prior predictions. So generally, we're kind of pushing towards models that have more black holes, more massive black holes than most models would predict. But I also think the takeaway of all of this is there is still a lot of uncertainty. Like these models are fairly simple, and there's lots of covariances between all these different parameters.
The distance and separation, is this distance to the binary supermassive black holes?
Oh, this is the separation. This is the distance to the black hole, and this is the separation between the two components. Yeah. Okay. I'm just going to very quickly finish up. So one possibility, of course, is that it looks so bright because there are multiple contributions to the background, right? So maybe there's a primary supermassive black hole binary background, but maybe there's a secondary background due to primordial gravitational waves or cosmic strings or something. And so how do we figure that out? So the most obvious way is to actually detect like two different spectral slopes in our gravitational wave spectrum. A student working with me named Andrew Kaiser simulated that and found that after about 20 years of data, we should be able to measure a second power law with amplitude roughly half the primary one. At about 50%, we should be able to get a fractional uncertainty, about 50% on the spectral index, right? And these numbers are the actual numbers don't matter too much, but the point is after about 20 years, we should be able to detect a fairly bright second background with a Bayes factor of like 100. So the 20-year mark will be interesting. Also, in about 20 years, we should start to see any anisotropy in the background. So supermassive black hole binaries at some level will not be isotropic. They are discrete sources. So at some point, we will see departures from that Hellings and Downs curve as we get more and more sensitive, right? Because they're single sources. Whereas something like a primordial gravitational wave background from early universe inflation, that should be, truly isotropic. And these histograms, I don't have time to go into it too much, but the point is after about 20 years, we should be able to see an anisotropic contribution to that gravitational wave background in about a signal to noise of 3, something like that. So the 20-year data set will start to be interesting. We also search for single sources of gravitational waves. We call these continuous wave sources. We obviously haven't detected any individual sources, but we can make plots like this. The red stars are our pulsars, and the color scale here shows the distance to which we're sensitive to a billion solar mass binary around our most sensitive frequencies. We haven't detected anything, but we're looking out to sort of 100 megaparsecs or so in most parts of the sky. There's some putative supermassive black hole binaries on here, either just because they're clusters, galaxy clusters like the Virgo and Fornax clusters, or things that actually look electromagnetically like they might be a supermassive black hole binary. Unfortunately, our sensitivity is very anisotropic. We're most sensitive in the directions where we have lots of pulsars, and very not sensitive in some other directions. And unfortunately, like most of these interesting sources lie in regions that were not that sensitive. So we need to carry out more pulsar searches, try to find pulsars to fill in all these parts of the diagram, and work with our international colleagues. One kind of cool thing that we can do is we can use electromagnetic observations of a putative supermassive black hole binary and actually use that to make our single source searches more sensitive. So this is a galaxy called 3C66b, and it shows these sort of like weird radio jets that have been suggested to be coming from a supermassive black hole binary. The period's about a year. The mass is predicted to be something like 800 million solar masses. This is the mass prediction. And this is our upper limit this is the mass that we get from our upper limit on the gravitational waves from this binary. This is just calculated in a couple of different ways, but this is our 11-year limit. This is our 12.5-year limit. Our 15-year limit should be even closer to this predicted mass. So we're slowly inching into regions where we should start to set like real limits or make a detection of these individual sources. And so finally, I'm just going to go through these like really, really fast. What are we doing to get more sensitive? So part of it, we're just continuing to do the same thing, right? With time, we're going to get more sensitive. But there's a couple very exciting developments happening over the next few years. One of them is not even the next few years, it's now. We are starting to use a wideband receiver at Green Bank. So our current data at Green Bank is from this radio frequency regime here and this one here. So we have 200 megahertz of band here and 800 megahertz here. And soon we're going to have this entire band with this new wideband receiver at Green Bank. And this is going to make us much more sensitive, in particular for tracking interstellar medium effects, which are frequency dependent. We're incorporating the CHIME data into our next data set, and CHIME observes every single day for most of our pulsars, whereas the Green Bank telescope observes once a month. So this is a residual plot with CHIME data, and you can see the yellow points are the CHIME data, the green and blue are Green Bank, so way more data. And for things that are radio frequency dependent, and in particular are more significant at lower frequencies, where CHIME observes that, like for dispersion measure, we get much smaller error bars on things like this dispersion measure. And if you're not a radio astronomer, we can talk more about this later, but this is a significant source of error for our timing experiment. So I'm really excited to see what CHIME is going to do, and we need a replacement for Arecibo. So I've been really pushing hard for this telescope called DSA 2000. This is a telescope that would be 2,000 small dishes. It would be built in a valley in Nevada. It would have about the collecting area of Arecibo. So it would replace Arecibo's collecting area and also be way more flexible. We'd see much more of the sky. We expect to get maybe a quarter of the time on this telescope if it's built. This plot shows the simulated population of single supermassive black hole binaries. Here's where we'll be by 2036 if we don't get DSA 2000, and these blue curves show where we'll be if we get DSA 2000. So it's going to let us like really dip into this population of these single sources. So I'm very excited for this telescope, and I really hope that it gets built. It's currently being funded by the Schmidt Futures Foundation, and there's also an NSF proposal that's being reviewed. So hopefully good news soon about that. It's being led by a group at Caltech. And we also need more pulsars, right? We want to grow the pulsar timing array. This is a simulated population of pulsars that will be detected with DSA 2000. So it will find thousands of new millisecond pulsars, which could be added to this array. And we think we can time maybe 150 millisecond pulsars with DSA 2000. This is work done by a postdoc at WVU named Ting Ting Liu. And she finds maybe 150 to 200 of them could be timed with the precision we really need to do gravitational wave analyses with them. But our total signal to noise is proportional to the number of pulsars. So the more pulsars we have, the better we're going to do. Finally, I just have 2 more slides and then I'm done. I know I'm pushing time. We want to build this next international combined data set. It's called DR3. We're in the midst of doing this right now. It should be complete in about a year or so. And that will have nanograph, EPTA, Indian PTA, PPTA data, plus data from Meerkat in South Africa. This is data that has never been included in one of the data sets before. CHIME data in Canada, and also data from a telescope in the Netherlands called LOFAR. So this will be an incredibly sensitive telescope. So all of the telescopes here, aside from the CPTA, we're still working to try to figure out a way to get our Chinese colleagues to join us in this effort. But all of these other telescopes are going to contribute to this data. And if you look at our projected sensitivity with this IPTA data, this is our sensitivity to these single sources. This is the projected sensitivity of our next data set in 2025. This is where that 3C66B single source sits, way up there. Do not walk away from this saying they're definitely going to detect this source in the next data set. There are huge uncertainties in the modeling of this source that lead to the mass estimates. But it's very promising. And these are simulated populations of binaries that are possibly detectable. This is from like 2 mass catalogs and kind of making different populations of supermassive black binaries. Anyway, very exciting. There'll be 115 pulsars, so way more pulsars than in our current data set. And of course, the ultimate aim of all of this is multi-messenger astrophysics. We want to detect single supermassive black hole binaries with gravitational waves. We'll also be able to follow them up with optical telescopes, X-ray telescopes, and really get a much more complete view of how galaxies have formed and evolved over cosmic times. And maybe other exotic sources of physics. We'll just have to see. But the next decade proves to be, I think it'll be very exciting. Anyway, sorry for going a little over.
Thank you, Maura, for a great talk. There are questions?
So early in the talk, you gave a nice little rule of thumb for the strain sensitivity of 200 nanoseconds over 15 years. And so that's improving by a factor of somewhere between 10 and 100 between the 2020 and 2030 projections. It looked like it was a really steep improvement. I wasn't sure if that was based on number of sources or if the timing sensitivity on individual targets is going way down or.
Right, yeah, so some of that, so going from like nanograph 2030 to nanograph 2020.
Yeah.
Yeah, so this, yeah, so it's way more than just the denominator is what you're asking. Yeah, so it's way more than just the denominator because we're assuming we're going to add more pulsars to the array. So we get, if we, double the number of pulsars, that gives us a factor of 2. We triple the number of pulsars, it gives us a factor of 3. And it also assumes this number is going to get smaller too. When we go to wider bandwidth receivers, bigger telescopes, things like that.
Okay, so like, how does the number of pulsars factor in? Because those two numbers that you give, the 200 nanoseconds and.
Okay, yeah. So this strain sensitivity, this equation here does not depend on the number of pulsars. But this is kind of just like a heuristic, but to actually calculate these curves, they depend on the number of pulsars. This is just kind of like, oh, look, isn't this cool? It like mostly works out. And the math is mostly, I mean, this is kind of, it's not crazy. It's not an accident that it works like this. Like the math generally points to this, but these are a lot more complex. Maybe, yeah. It's a good question though, because this doesn't at all explain that increase in sensitivity. Yeah.
What are the prospects if any of different gravitational numbers?
Yeah, so we have a group in NanoGrav that is looking for bursts with memory. So these are gravitational wave events that basically leave a permanent imprint on space-time. Every gravitational wave event leaves a permanent imprint on space-time. So a merger of a supermassive black hole binary will permanently distort space-time. This in our gravitational wave data, this will basically look like a step, not our gravitational wave data, sorry, let me step back. In our timing residuals. So if we look at one of these timing residuals, a memory event will basically look like a step function in the residuals. And so we have a group that's working to search for these. Also looking, there should be correlated signatures among all the pulsars. It's not predicted we should see them yet if you look at kind of reasonable expectations for their amplitude. But our last, we have a group working on a gravitational wave memory analysis of this data set. And there are other papers you could look at with upper limits on memory effects. Yeah, it's pretty cool because it's something that's kind of unique to the PTA regime. Like if we could detect that, you can't do that with molecular.
I was wondering how much of the sort of independent common red noise is captured in the spatial correlation.
Yeah, so you mean, in that Hellings and Downs curve?
I mentioned early on the detection of the observation of a common red noise process.
Yeah.
We expected that to be stochastic gravitational waves. So how does that measurement, how did that fold into the spatial correlation analysis?
Yeah, so we kind of have like two different steps of the analysis. One is just completely spectrally based, where we model each pulsar with this common noise and the independent noise. And then the Hellings and Downs curve that we're observing, like this thing, this is the correlated power, both for like auto correlations and cross correlations, basically. So the auto terms are in there as well. Does that make sense? Like we.
I mean, so the model enforces all of it to be.
Yes. Yeah, there's really no, well, there might be a good way, but we do not have a good way right now to discriminate those when we do this correlation analysis. Back there and then.
What
the spin frequency of the pulsar? Basically none. I mean, we're averaging over, say, a half an hour to get one of these pulsar times of arrival. So whether it's a 1 millisecond pulsar or a 1 second pulsar, doesn't really matter. It matters, of course, for the narrowness of the pulse and how well we can time it. So like pulsars with short periods just have narrower pulses, and we can measure their times of arrival more precisely. So it comes into the like the errors on our times of arrival, but the frequency itself doesn't really matter.
So you can just extend it to like much more pulsars with longer periods because the sensitivity will be like, because the timing error would be much larger and they won't be useful.
We find that if pulsars have TOA, time of arrival errors, bigger than about a microsecond or so, then they just don't matter. Like they just don't contribute to our gravitational wave sensitivity. So we could just throw every pulsar we know of, even the 1 second ones, into our analysis, but only the top 20 or 30 really matter anyway. I mean, so just there wouldn't be any point. With a really big telescope, like if we get this square kilometer array, then we might be able to use pulsars with much longer periods, because with the big telescope, we'll be able to time them more sensitively, even if their pulse widths are, longer, they have more noise. But right now, yeah, there's just like no point.
Yeah, final question.
I wanted to ask one more time about the single source evolution of cluster
Yeah.
programs. So obviously you can measure the period evolution, but do you think you could measure the eccentricity evolution?
Yeah, so far, all those plots were for circular binaries. Eccentric sources will evolve faster. So yeah, I guess in some scenarios, you might see evolution of the eccentricity. But even so, you're probably familiar with this being in nanograv, but a postdoc working with me named Loki Day, he and Abu Manat, anyway, there was a paper recently published on searching for eccentric binaries in nanograv data, and they still model them as non-evolving eccentric binaries because for most of their regime of sensitivity, we still don't really expect the eccentricity to evolve much over the 15-year time span. But I guess for very eccentric sources, maybe it would. I don't know.
A gas list?
Yeah.
I mean, even 30-year data, right?
Yeah, maybe, yeah. Yeah, I mean, all of this is so much work to do in this area, as you know, just trying to figure out where to focus our efforts. Do we try to search for that one really weird but really bright source, which might be evolving over our time span, or focus on where we think most of them will be, non-evolving sources? It's tricky.
It's too bad that OJ287 is not in a good place.
Yeah.
For sensitivity.
Yeah, it's a real pity. It's kind of lying in a very empty region of the sky where we don't have many good pulsars.
Is it this lack of southern hemisphere telescopes, or is that because it's off the galactic plane?
That's the galactic plane. That's the main thing. If you look at this plot, most of our pulsars are over here, for a couple of reasons. One, Arecibo observes over here. So Arecibo has found many of these. And then most of them are just towards kind of, the general region of the galactic center. Most pulsars do live in that region, but then there's an additional bias just because most surveys have looked in that region. So yeah, there may be more pulsars out here. We just need to search for them. And of course, our colleagues in the IPTA, it's a little bit better when you include all of the IPTA pulsars, but not much. So we get some down here, but you still see there's just way more in this part of the sky. So the international collaboration doesn't solve it entirely either. Yeah, unlike LIGO, we can't put them wherever we want. We've got to deal with what we've got.
All right, let's thank our speaker again.
Thanks for all the good questions, everybody.
Thank you.